linear algebra and in group theory, it's something that maps to the zero codomain. And
Yes.
this one doesn't seem to follow into that. So I'm not sure whether it's the naming or am I.
Good questions. I'll start with answering them. Uh, I'll start with answering them. Any other questions? Ayub and Charles?
Yeah, I think we get along with Stanley. So we rather go by what he's saying right now, so that we don't overcrowd these questions. I think
No.
I also had problems with
These
the.
are very important questions. Very important questions. And yes, there is a connection. He correctly pointed out about the kernel, and there is a connection, and a very serious connection is there. And yeah, so in fact, I plan to do it in that way. Okay, so I'll do that. Yes, Charles and Ayub, I sent back your message. Uh, just quickly, because Ayub's question that which he sent me was very short. This is obviously A union B minus A intersection B, which therefore means intersected with this, but then this means using the complementation laws, this is this. Now you
Good
see.
evening, Doctor.
Yeah?
Are you sharing the screen?
Did I not? Oh, okay.
No.
Okay.
Not yet.
And please record.
Yeah, I've started recording. Okay. And so you can see now, I believe.
Yes, we can.
Okay. So now you see the symmetry immediately suggests this is symmetric in A, B, A complement, B complement. So if you replace AB by A complement, B complement, it comes immediately to this. Right?
It is as clear as daylight, Doctor.
Okay. Alright. Now coming back to Stanley's question. So I erase this. I start with the definition with the intuitive notion of a function that we were drawing. If we have a function from x to y, its stock diagram, if we draw its stock diagram, it looks like this. That is a general function. It looks like this, where these are the points whose stocks are shown, and there could be some points, okay, which are not mapped. Remember that these points are all taken into this point are taken into this. Now if you see, this means that the whole set X have been partitioned immediately into these stocks. So I have a partition over here, and therefore there must be an equivalence relation, and that equivalence relation is precisely, so if this is y and these are points, say x and x prime, that is exactly my kernel pair relation. So x is x prime is said to be in the kernel pair of f, if and only if fx is equal to fx prime. So which means it is in this. So kernel pair of f is nothing else but the partition given by the partition induced by the function f. So you see, every function actually gives you this partition, and that is the kernel pair relation. Okay? So, is this intuitive picture helpful now? Yeah? Okay. Now...
Sorry, Doctor? Can I ask a question?
Yeah.
This set X that we've got,
This?
are there also other points that are not mapped onto Y?
No. There could be some points mapped to y, some other points mapped to...
Sorry, not to the small y, to the set Y.
No, you know that for every member of X, there is an image. The reverse is not true. Right? That's the whole point of a function. Everything in X has an image. So it is mapped to... So every member of X is in some one of these stocks. Obviously, here I meant that X has only 1, 2, 3, 4, 5, 6, 7, 8, 9 points only. But yeah, you know, this is just a picture.
Yes. So there are no other points that are sitting in X, in the set X.
Yes, exactly. There are no other points in this diagram.
Yes.
Okay. So now you see, this is the intuitive picture of kernel pair. Now connection with kernels and so on. So now suppose X and Y are groups. So you have a function from X to Y. It is called a group homomorphism, provided there is this, it preserves the multiplication. If the multiplication in X is denoted like this, then this means it is something like this, right? And obviously you have f1 equal to 1. That follows from here. The left hand side is the multiplication. This is the multiplication, group multiplication in X. The right hand side is the group multiplication in Y. This one is the identity in X, and this is the identity in Y. Okay? Now, there is something nice about groups. You see, the one element set, although I write like this, I should write like this because that's how we said we would denote the one element set. There is obviously only one group structure on this, and that is multiplication is this. So the empty set, the element, the only element, that is its identity. Okay? And for any group X, you know there can exist only one map from any set to this, and that we denoted by tau X. That is obviously a group homomorphism because every X is being taken to that single point. So tau X, XX prime, this is also that single point, and that is obviously this. and obviously the 1 is going. There is no problem with that. But there is a unique element also. There is a unique function. This is unique, we know. There is also a unique function. What does it do? There is only one element, which is its identity. If this has to be a group homomorphism, then there is only one way in which it can be a group homomorphism. It must take the only element to the 1 over here, and that's a group homomorphism. So there is always a group homomorphism from the one element group to any group. Okay? And therefore between any two groups there is always at least one map, one group homomorphism, which is the composite. And strangely we write this as the 0 map. We write it like this: 0 with y it's equal. So what is this doing? This takes every x. First it gets only to one element and then it goes to 1. So every x is going to the identity of 1. So that is a trivial homomorphism. Okay? Now let's see. Suppose we have a group homomorphism. So what's the kernel? X belongs to the kernel of f if and only if fx is 1. But remember, there is this other homomorphism also. This is this 0 map evaluated at x. So this is if and only if fx is equal to this, right? So it turns out that there is some kind of relationship, but indeed it is much more. It is much more. If we look into this kernel, and the story is a little more deeper, and that is this: the kernel of f is a normal subgroup. The second fact is that the kernel of f corresponds to, if we look into kernel pair of f, which is what we have looked at it now, there is a correspondence between kernel of f and kernel pair of f. And this correspondence is much more deeper, and it goes a little more into group theory to say about this. These are called congruences. And congruences are special kind of equivalence relations. Observe that this is a subgroup. Your x cross x, this is not only a subset, this is a subgroup of x cross x. So congruence is nothing else but a relation on x which is also a subgroup of x cross x. X cross x, what's the multiplication? Multiplication is component wise. And it is to be shown, it is shown that congruences on a group, they exactly match. So the correspondence is congruence on x, they match with, they are in one-to-one correspondence with normal subgroups of X, and these match with kernels of group homomorphisms. So it's a three-tier kind of a thing. Now, the question that Stanley asked, is there a connection? Yes. When there is no, so using this equivalence, we can therefore think of kernels as nothing else but some congruence, and congruences are nothing else. In fact, there is another one which is kernel pair of group homomorphisms. So kernels of group homomorphisms are nothing else but kernel pairs of group homomorphisms. But you see the existence, so that means what is the kernel pairs of group homomorphisms? These are those points x, y such that fx is equal to in fact we could have written it over here also. So you see, so this is the reason why I said so. So there the connection lies. Now when you don't have a group operation, this works for groups, this works for rings. As you said, you don't have normal subgroups, you have what is called ideals. They work there also, but they are not going to work for say, if we proceed, we will see there are structures finer than groups which are called monoids, for instance, but they are some kind of omnipotent everywhere. So they don't work for monoids, they don't work for several other structures. But where kernel pair still works. So we don't have a way to speak of this kind of a relationship, something like this or something like this in case of general sets, but we can speak about something like this, and that takes up the position here in the general sets. So kernel pairs are essentially, and therefore that's why the name kernel pair, because you are taking this pair of objects, so that's why this name kernel pair. And well, you can think of as if we are in just the previous stage. If you look up or try to interpret this equation in groups, say, or in abelian groups, fx is equal to fx prime. So that means fx, the inverse of fx prime would be 1, but it is if inverse of fx prime is f of x prime inverse, and then f of x prime inverse is 1. So x prime inverse belongs to the kernel pair and so on, kernel of f and so on. But we don't have this way to bring this in general sets. We don't have a way to bring this fx prime on this side, on the other side of the equation, and have a 1. So we have to stop here, just stop here, and that gives us our kernel pair. Yeah. So you see, there is some connection. Yes, there is connection, and the connection is in fact a very deep-rooted one. And Yeah, so yes, do you get this, Stanley? And others also.
Okay, thanks, Doc.
Yeah. So now and then the next part of the question is, what is the point of comparing? So next point is, what is the of comparing surjections? Well, this is also a very good question. What is the point of comparing injections? That you understood. Well, injection simply means that you are it's kind of saying that this set is being put inside this. So it's some kind of getting bigger and bigger and bigger. Right? So this is about comparing injections, right? So if this is X, Y and Z, well, this idea that this is getting inside this by an injective function, this is getting inside this by an injective function to say that X is smaller than Y or Y is smaller than Z and so on. All this idea. Very good. Now, as I said, if you have a surjection, what does it mean? If you go back to this diagram, it means that you don't have these points. Right? Everything has a pre-image. So, as we knew already, that the moment we have a function, there is a equivalence relation. There's immediately an equivalence relation on the domain. The moment you give me a function, there is an equivalence relation. So what is surjection actually doing? Surjection is kind of gluing these stock points to this point y, these stock points to this point y prime, and this one to this point, this. So what is the idea? So idea is just the opposite. You have certain partition over here, and you are, so 1, 2, 3, 4, that's what you are doing. So this, all of this is being glued to this one. All of this is possibly getting glued to this one. All of this is getting glued to this one, and all of this is getting glued to this one. Then you are gluing these two. Okay? So these two are going to get into another one. 1, 2, 3. So these two get glued here. Then this is going here, and this is going here, and that's it, and so on. So X, Y, Z. Now you have surjections. So you see, to glue, when your surjections, so the composite is actually gluing. So the moment this, what is this composite doing? So this composite, so it is first gluing this and then gluing these two, right? So this glued thing remains as it is, this glued thing remains as it is, but these two separate partitions, which were separate here, are now further glued to this in Z. Okay? So remember the first day when I spoke about this sushi thing, right? You have several kinds of dishes of fishes, right? But some fish dishes are put on a pink plate, some on a black plate, some on a blue plate, and some on. So that's the first stage of blue. Now the pink and the blue have the same price. The black have another price. The green have another price. So this is the next level. So when it is coming to pricing, he is looking into the composite gluing. It doesn't matter what fish you have actually eaten. It doesn't matter. So that's how they operate. So it's a two levels of gluings that are going on, and that is exactly what a surjection is. So when is a surjection? So we definitely, therefore we can say that a surjection should be bigger. So a surjection going out of, if we, so that's how if you remember the surjections we said. So if you look into this as Z, right? So we said that, and this is your G composed F. So this surjection, when you have this map, if you have this map, then this X was bigger than this Y, because here bigger means you can glue things in X to get Y. Okay, so these were surjections. So you can roughly think of that this is some kind of saying that this is bigger. I wrote it like this to differentiate from this. Let me not write this. It's not about cardinalities. How should I write? Let me just write like this to say that, well, you can. So this means that X is bigger than Y. That means there is a surjection from X to Y and so on. Yeah. So this is the idea behind surjections. Okay, and comparing surjections. So comparison of surjections mean that whether from the bigger one you can glue certain things and get your smaller one. Yeah, so that's the meaning of the surjection. Is this clear?
Yes, Doc.
Stanley?
Yes, maybe the question is in the element of X. You put in partitions. For that partition can have many other things in it, which are mapped to one point in Y.
Yes, there are several points over here which are mapped to this. There are several points over here which are mapped to this. There are several points over here which are mapped to this. So let's take an example that we have seen, for instance. So let's take this. Let's take this example. Say, say from reals to 0, 1. Let's take this or this minus 1, 1. This very well-known map. Let's take the sine map. Okay, so if we try to draw this function, it looks like this. This is minus 1. This is 1. And let me try and draw it. Well, it's a difficult thing. And then it will go on in the same way. And so on. So now, obviously, well, you have to pardon my drawing. So if you fix any y over here, so let's see what is this solution. So solution of, we want all these points x1, x2 and so on, x3 and so on. So solutions of this equation, sine of x is equal to y, where y is something between -1 and 1. Now given, I mean, assuming this fact that since this is so using since this function, since sine is surjective, there is a theta, say between -pi and pi. Why should I take -pi? I can make it like this, such that y is sine theta. So this is this old question, sine x is equal to sine theta. So this means sine of x minus sine of theta is 0. So this means 2 sine of x plus theta by 2 and cos of x minus theta by 2 is 0. So this means either sine of x plus theta by 2 is 0 or cos of x minus theta by 2 is 0. So this we know. So this tells us x plus theta by 2 is some n pi, or x minus theta by 2 is some odd multiple of pi, pi by 2, where n is in z. So this is in fact if and only if. So if and only if x is 2n pi minus theta, or x is 2n plus 1 pi plus theta for some n in z. So we can write this as x is some n pi plus minus 1 to the power n theta, where n is in z. Right? Remember this simple trigonometric equation which we solved in, say, high school. What does it therefore say? This says many things. Firstly, it tells us all the graphically it tells us all these solutions. Okay. Secondly, it tells us, it completely describes the kernel pair of. So it completely describes the kernel pair relation of sine. How is it? We know that sine from minus pi by 2 to pi by 2, this is a bijection. This is a bijection. So what is it? X prime belongs to the kernel pair of sine if and only if x, you can write it in this way, that how do I write it? Well, from here, how do I? Okay, so there exists a theta between minus pi by 2. So there exists some n and m in z such that x is n pi plus minus 1 to the power n theta, and x prime is m pi plus minus 1 to the power n. So you see, solutions, you see so many things are coming up at the same time. Solutions of these equations that we have done actually are nothing else but this abstract way that we are saying of depicting or characterizing the kernel pairs. Right? Is this clear? Is this any question?
Yeah. Okay.
Yeah?
Can you just go a bit 4 lines from the bottom there?
Yeah?
Where it is written x prime is an element of the kernel pair there.
This
And
one.
then there's a sign.
Yes. Remember,
Yeah.
kernel pair
That
of
statement
F.
complete.
Kernel pair, yes. Yeah, what is it?
Yeah, I'm saying is that statement complete?
Yes, remember.
On the sign.
Yeah, you see, I'm using this 3-letter thing sin as the name of the function. So this is the function, right? I used this also as the name of the function. Instead of writing as f, I just wrote it as sin. So that is the sin that I committed earlier. So if you are pedantic enough, you would instead write like this. Right? And then you would have kernel pair of F. Okay? So in the symbol, it is that kernel pair and that name of that function F. That's how we are denoting it. Is it clear?
Yes, it is now, Doc.
Okay.
Sorry, Doc, just one question.
Yeah.
This graphically, where would the theta function be?
Yes. So this theta, so given this y, there exists a theta in between minus pi by 2 and pi by 2. So there is some point over here for minus pi. Minus pi by 2, it's minus 1. So this point is minus pi by 2 and this point is pi by 2. So this is your theta, right? In this graphical representation.
Yes, that is correct.
Yeah. So that is our theta. So you see, this simple calculations that we did in our school life, they are very important. they give rise to these abstract notions. These abstractions are essentially those so you're trying to find out solutions of these equations. That means you're trying to find out actually kernel pairs of certain functions. Do you get it? Obviously, I meant equations like this. So every such equation like this was actually aimed at telling what this kernel pair is about. Clear? Yeah? So should we proceed? Or you have still more questions?
I think we should proceed.
Okay.
I'm not sure with others.
Stanley? Are you?
Yes,
Yes,
I think
we
my
proceed.
questions were answered.
Yes. Stanley?
Yes.
You were saying something?
No, I did say my questions were answered, so we can proceed.
Okay. So, now coming back to this issue. So we have ways. So we have seen we can compare surjections or injections. Both of them there are ways to compare them, right? We know which is a bigger surjection, we know which is a smaller injection, and so on and so forth. Now injections mean essentially they mean subsets. So this comparison of injections thus lead to comparing relations. Because relations, what are relations? Relations on X, which are nothing else but subsets of X. So a relation is bigger if it is as a set bigger, and hence compare equivalence relations in particular. So for instance, on a set X, if R and S are equivalence relations, these are equivalence relations, you can even take them relations also on X. What is the meaning of R being smaller than S? Precisely the meaning is R is a subset of S. So what does it mean? Explicitly it means if X are Y, then it implies X S Y. Okay? So that's the whole idea. Okay. So now suppose we have, so assume R is an equivalence relation. Okay. Now I am going to give you a, so remember, since it is an equivalence relation, it partitions X. So we have its equivalence classes. So this is its factor set. And what is this? Each one of these X, so we write like this as if to say X divided by R, as if something like that. So this is precisely the collection of X prime in X, which are in the same partition of R, same partition as X given made by R. So it means X R X prime. And we know that these are our, so the picture is like this. So the moment we have an equivalence relation, we have a partition like this. So this is some X by R. So here is some X, X prime. So this partition is X by R, this partition is Y by R, and so on. Okay. So we take, so over here according to this diagram there are 1, 2, 3, 4, 5, 6 partitions. So the factor set X, capital X by R, has only 6 elements. Okay. So we therefore get hold of, so these 6 elements. What do we do? So this partition gets mapped to this. That's exactly what I was saying about this gluing. This part map goes to this. This one goes to this. Everything over here goes to this. Everything over here goes to this. And so on. So that gives us our factor map. So what is it? From X to X by R, this is our factor map. This is the Greek letter nu. It is written like this. It is called NU. It is the Greek letter for N. So it goes to this equivalence relation, equivalence class. Okay. Obviously, this is surjective. This is called the factor map. The factor map. Mu R is surjective. And I'll not prove it. I hope you can do it. Because if you take any member, this is the set of equivalence relations. So any member over here is nothing else but the equivalence class of a member from here. Okay, and that is where it is. That is where it is coming. So observe this Y and Y prime. Both of them have come to this, right? So you know how to get hold of a proof. So you'll have to write this, but it's just a description. So it's a surjection. Okay. So given an equivalence relation, there is a surjection. So now let's see. Suppose we have two equivalence relations, R and S, and I am saying that R is smaller than S. Okay. So due to R, I have this equivalence relation. So this is my nu R. And due to S, I have this equivalence relation. So I have this. So both are we know both are surjections. That's why I have those double arrows. Okay. Now let's see. So here is the formal proof. Suppose x and x prime are related to R. So this means I have x prime related by S also. So in other words, that is x by R, if you look into this, this thing gets to be so what do you expect between x by R and x by S? So that's my issue. So to fix
Subset.
out which one is the subset of which one?
So the R subset of S, exactly the same relation as above.
Okay, so you're saying this.
Yes.
Yeah, good. So what can you say about so therefore since it is like this, I can define this map. I can define this map F. What will F do? F will take the equivalence relation due to S to the equivalence class of X due to S due to equivalence relation to R. Let's see if I'm right. Why? See, I'm saying this. So there is a question which is usually in textbooks written to see, to check F is well defined or not. What is the problem over here of well definition? Because you see x by S, if x is equivalent to x prime, say, let me write x1. So this is, in this case, this is exactly the situation when x by S goes to, this is equal to x1 by S, right? Okay? Now see, there is a problem with this. If I define something using this element x, what is the well-definedness problem? The problem is that this one, by my description, is going to the equivalence class of x by R. This one, by my description, is going to x1 over R, the equivalence class of R, of x1. Now, unless, the problem is, are they equal? You see, this tells me that my direction was wrong. You see? This tells me my direction was wrong. Okay? Why? Because I know that x and x1 are related by S. But I don't know whether they are related by R also. Okay? So this may not be equal. So this equality is a question mark. On the other hand, if I do the same thing with R, so let me put the same thing. over here. But now I change my this to R. Okay? And each S I change to R. And each R I change to S. So I interchange this. Now you see in this case what happens. Since X is related to X1 by R, it tells me that X is related to X1 by S also. And this therefore is saying that this is equal, these two are equal. So it's actually not this, but this. So the relationship is actually this. So the equivalence relation, the equivalence class of X under R goes to the equivalence class of S under R. Okay? So that is, and so you know. Now let's try and figure out things. How is so? This is surjection. You are saying that this is bigger than this one. How is it possible? Let's try and think. Firstly, intuitively, R manages to glue something, but S manages to glue something more. So therefore, you expect that there are, when you are dividing by something less, you expect the quotient is bigger. So this has many more elements, and this should have small number of elements. Yeah. So you see, this is expected that this should be bigger. Now let's try to figure it out using our intuitive diagrams that we have drawn. So the scenario is like this. We have X and we have R. So this is what I am drawing, is the partition due to R. Now what does S do? S, so this says these are related by R. What does S do? S actually produces, so whenever two things are related by R, they are also related by S. So S is something like this. Okay? Now can it cut? Can it cut like this? Well, if this was another partition, if this was another partition, then you are telling me that in particular this element and this element, although they are related by R, they are not related by S, which is in contradiction. So it is S is not, it cannot cut an R partition. So this is not the picture. So what is the picture? So that means if it is bigger than one equivalence, R equivalent, this glued part, if it is bigger, then this one must actually take in also this next one. The moment it takes. So the things that S glue are then nothing else but joins of these equivalence classes. So you see, you get this picture. So the S equivalence relation looks like this. It partitions things like this. Possibly this one is maintained as it is, and this one is glued, say. So you see, so in effect what is happening? In effect, 1, 2, 3, 4, 5. So in x by r you have these 5 things. Now when s comes into, so this is your x by r. When s comes into the picture, these two things are glued by s. So that is going to produce then another equivalence relation on this. This third one is kept as it is, and these two are glued. So that gives rise to our x by s. So obviously, this is my, if you remember, this is your y by r. But here this becomes your y by s, which is also equal to x by s. This is your x by r. This and this are glued and they become the same. So you see the picture now. Yeah? So many things, the equivalence classes of S are, so this is your mu r, this is your F, and this is composite is your mu s. You see this? Yeah? Questions? Comments? Queries?
I think this picture makes it clearer for me.
Good.
Much clearer.
Good. So you see, as you increase your equivalence relation, you are actually gluing more and more and more things, right? And so your equivalence classes are getting smaller and smaller and smaller. So that's the idea. Okay? Now what did we say therefore? We said therefore that if, so what did we say? If R is smaller than S, then remember, as surjections it was this mu r. Mu r, this is the surjection. Remember, we were comparing surjections, so this is bigger. So mu r is bigger than mu s. Okay? So that is one side of the story. This is number one. So as surjections, mu r is bigger than mu s. So the quotient set is bigger, and this is exactly what you all agree. So now I am going to say that in fact the converse is also true. But strangely speaking, I'll not take the usual route. I'll not take the explicit route. And I will take another route. I think I developed that later on. Okay. So now suppose, I'll do the other side. So suppose now I have two surjections. One is F and the other is G. And I am saying that f is larger than g. So which means that I have a map like this. Now I look into the kernel pair of f and the kernel pair of g. Okay? So, suppose x and x prime belong to the kernel pair of f. So it means this is exactly saying fx is equal to fx prime. But I have this h, so this tells me since fx is equal to fx prime, h of f of x is equal to h of f of x prime, which is same as saying gx is equal to gx prime, which is therefore same as saying that x prime is in kernel pair of g. So whenever I have this, I have the kernel pair also like this. So what I prove therefore is f is greater than or equal to g implies that the kernel pair of f is smaller than the kernel pair of g. Okay? Now I make a mixture. So why do I make mixtures now? So what do I, so the situation is like this. I started off with equivalence relations on x. Okay? And the other side is surjections going out of x. On one side, what do? I take the quotient. So so r, so take quotient. So r is being taken to new r. Okay? And the other side, if I have an f, I take it to its kernel pair. So this side is take the kernel pair. Okay? So what are the two things I have taken? I have already shown this. If r is less than or equal to s, then it implies that mu r is greater than or equal to mu s. And if f is greater than or equal to g, then kernel pair of f is smaller than the kernel pair of g. Okay. Now let's stick it. So suppose I take an r and I take an f. So let's start with this. So suppose I say, suppose I take an r and I say it is smaller than the kernel pair of f. Now the question is, what is the factor of this? So this tells me, so firstly, what is this? So this is, if you remember, this is going to x by kernel pair. So it's taking to the this equivalence class. So this tells me that mu of r is bigger than mu of kernel pair of f. So what does this whole story mean? This means that this was your mu of r, this is your x by r, and you have, this is your x by kernel pair of f, so this is your x by kernel pair of f. It means that there exists a map like this. Okay? So that is the. Now, if you have this, so see the next line. If you have this, then it says the kernel pair of nu r. Aha, now what is the kernel pair of nu r? So let's see. X prime belongs to the kernel pair of nu r, if and only if nu r of x is equal to mu r of x prime. And when does this happen? This is precisely the situation when the equivalence class, R equivalence class of x is same as the R equivalence class of R, x prime. Okay? And this happens precisely when x prime belongs to R. So, kernel pair of mu R is nothing else but R itself. So, this second equation therefore immediately says the kernel pair of nu R, which is R, is smaller than the kernel pair. Now you can see that therefore this is nothing else. So you see. So this becomes a very nice rule, right? You start from R, you go to nu R, and you can come back, and that satisfies this nice rule. R is smaller than kernel pair of f if and only if the factor map due to R is larger than the factor map due to this, or in other words, the quotient set by R is larger than the quotient set by this. Okay? And this sets up this correspondence. What is the correspondence? That I am going to say that therefore there is a, if you go back, so you see that this is a bijection. right? You go by, start from R, take quotient, and go back, you get back the same thing, R. On the other hand, if you start with F, you go to its kernel pair. Aha! Now there is a problem. I come to this nu of kernel pair of F. So my question now comes, how are these two related? Well, I'll just now show that this is nothing else but this as a surjection, this is equivalent to F. Okay, so that's the last straw that we are left with. So x, this is your x by kernel pair of F, and you started off with your this thing. Okay, and this is new kernel pair of F. Now let's recall this again. So let's copy this, because I'll use one side of the story. I'll use this. So in particular, if you take R equals kernel pair, so therefore nu of, so R is kernel, how do I do this? No, I think I have to do this explicitly. I don't have the machinery to do this directly. Okay. So let me take x and x prime. In kernel pair of F. Remember, this means that x, the equivalence class of this, is equal to the equivalence class of this. This is if and only if it is this. This means that fx is equal to fx prime. So what do? I define this function. Define h of to be just fx, and this relation, this computation therefore tells you, if you took another representative instead of x you took x prime, and they are same, then fx is equal to fx prime. So this is a well-defined function. Okay. Now I am going to show that H is a bijection. How? For each y, if I take y from A, this implies that there exists an x from x such that y is equal to f of x. Okay? And so this means, if you look into this equivalence relation, this class, everything which is mapped onto y is actually in this equivalence class. And h of this is equal to f of x, which is y, and is the unique element of, remember I am not working with members of X. These equivalence classes, these are all the things that have the same value as X. So therefore that has been now represented by one single point. So unique element of this factor set such that its image, H image, is 1. So for each Y there exists a unique member which makes this H of Y is this. So this is a bijection. So remember, in our comparison of things, so therefore we can say that F is larger than mu of kernel pair of F, and that is larger than this, that is F is equivalent to mu of kernel pair of F. So the end story therefore is that there are two ways of looking into this. So you see, the end story is either you look into equivalence relations on X, or you look into surjections going out from X. They are one and the same thing. And what is the machinery, or what is the tool to convert? Well, equivalence relations, you take it to the factor map. And if you have a surjection, take its kernel pair. So that is the recipe. Moreover, it satisfies this condition, which is actually a convenient, how should I say, abbreviation of these two these two conditions, right? So this is the crux. So that's why this is the summary of the whole situation. As you saw, comparing injection gave us ways to look into things which have more and more elements, and comparing surjections give rise to the idea of equivalence relations, and these two, so surjections are same as equivalence relations. So this is the thing that is established now. So there are two versions. One is equivalence relation and the other is counting, right? Having more. So these are essentially the two things that you have for functions, and two basic processes in sets. But with that, I'll stop here today. I'll ask for your questions. This is essentially what is there in this section 8, and there is a little more in 8.2.1 saying that this is natural. This equipotence is natural, and so on and so forth and so on. So I hope that part will also be clear to you once you go through this, what I said today. So we will spend one more class, or possibly two more classes on this, on up to section 8, because firstly I'll say why after I have answered your immediate doubts. Yes? Immediate questions, clarifications, doubts?
Mine is not a question, Doc. I just wanted to scroll again to the last sentence. I did not get it properly.
Which one? This?
Of your slide. Yes.
Yeah. Yeah, which one did you not get it?
Oh, the H image one, the last one.
So you see, what I took was, I have to show that it is a bijection. So what do? I have to show that if I take any element from here, I get one and only one element from here which is mapped by H to this, right? Right? That's the meaning of a bijection, right? Each element of the codomain has a unique pre-image. That's the meaning of it. Remember those three diagrams. So the stock of a bijection always looks like this. So everything over here that you take, you will have a unique pre-image, right? So that's the idea behind a bijection, correct? Yeah?
Yeah, it's clear.
So what do? I take a y from A. Now you have told me that F is already a surjection. So if it is so, then that means everything has a pre-image under F. So there exists an X such that y is equal to Fx. Now I don't know how many such small x's are there. But what is this equivalence class? This equivalence class is precisely the set of all the members of X which are mapped by F to Y. Right? So, what do? I therefore take this equivalence class of X, for which this X that I could take, and I know how to map H. It is so map of so Y is actually an H image. But I am saying this is the unique one. Why? Because if I have any other member of this factor set. Now remember, how was this factor set constructed? This factor set was essentially, if you go back, this factor set, so this is the kind of picture, right? So the factor set had this one in this example. This is one element, this is another element, this is another element. So this was a Y. You have taken this. Now this element in the factor set doesn't go to Y, because you have already collected all those which go to Y into this equivalence class, right? So therefore, this one which you chose, this equivalence class which you chose, is the unique one which is taken by H to Y. There cannot be any other else. So therefore this is the unique one, okay, whose H image is Y. So what you have done, you have taken any element of A, and for that element you have found a unique element of this factor set of X by kernel pair of F, whose H image is that Y. So therefore this is a bijection. Is it clear now?
Yeah, it is clear now, Doc. Thank you very much.
Okay. Others, Stanley and Ayub?
I'm covered, Doc. Thanks.
Yes, Doc, I'm good.
Okay. So I would still now urge you to look after this lecture. I would still now urge you to look into that section again. So you see, it is pretty deep waters. So we are no more close to the shore. So the thing is, there are two components. One is this injective map, and the other is this surjective map. And we have shown that every function is a mixture. It has a surjective part and it is an injective part. Okay. So what every function is doing, it is essentially trying to glue some elements, and then on the glued part it is putting it inside another bigger set. Okay. So this is essentially what general function is. So you should get this picture very, very clear. Okay? So if you try to draw it, it would be something like this. So what is it doing? The stock diagram tells everything. So this is the surjective part. This is the partition. This part is the surjection. Okay? And this part is being injected inside this bigger set. Okay? So this is the general picture of a function. So there is some things are getting glued, and then after the gluing process is done, things are then injected inside a bigger. Okay? Now this suggests therefore this correspondence between equivalence relations and surjections and so on and so forth. But there is yet another thing which this one opens up. It seems therefore that there is a bigger demand for studying relations like this order relations. Okay, we see it again and again coming up. And this I am writing as the other way round, greater than or equal to. But see, this relationship is again symmetric, reflexive, transitive, and antisymmetric. Right? Same over here. So we need to study these relations. So the next time, once we get a grasp of this, the next thing that we are going to do is to study these relations. So relations which are reflexive, transitive, and antisymmetric. In fact, we saw in both the cases of comparison of injections as well as in surjections, we have reflexivity and transitivity. We don't exactly have the antisymmetry, it is some kind of an equivalence and so on and so forth. Such things are known as pre-orders. And this is when we have antisymmetric pre-orders or partial orders. So we will start off now studying not a single X, but a set X equipped with a pre-order relation. So now you see it is just not a collection of things. It is an extra structure that we are bringing. You'll ask why this extra structure? The answer is already here. You see that putting an extra structure often brings much more light. Often brings in much more light to understanding the place where we bring that structure. Yeah. So this is not new. This is not new. Why do we arrange our furniture in our room? We need a bed to sleep. So, and we can keep it anywhere where we wish in the room. That's it. But why do we have to keep a bedside table just beside it? a lamp on the bedside table, and all of these things, to connect the lamp there should be a nice plug point near the bedside table, so the bedside table must be there. Now we need a fresh air, so this bedside table must not be obstructed. What is all this? And the moment you do all of this, it becomes a bedroom. But if you stuff the room with a bed, with a bedside table, with a lamp, anywhere, it doesn't become a bedroom. Right? So you need some structure gives a way to understand the role of, understand individual elements, individual things better. Okay? So now we will be moving into things which are structured. So the first kind of structured things is this order kind of a thing. And we will see there are many nice observations we can make just by seeing it is a pre-order or a partial order. Several things come up from here. And this will give rise to study of other structures. So we will see, we will all take this through pre-order, partial order, then some kind of a completion process will bring us to something called semi-lattices, and that will bring us to something called commutative monoids. And that will bring us to groups. And I've written up two things. I think this, I plan to write this part on groups, this part on rings, where we have two such things, and then merging. So groups along with an ordered structure, they are often called partially ordered groups or partially ordered rings, and then using them to describe our numbers. So it's a host of things. Okay, you will see now, once we have come to structures, you will see the next part is also getting, there is a pattern slowly emerging, slowly, and a pattern will emerge. So the next parts will also get a little, I'm not saying they are simple things, but your experience with these previous things and then what is coming will make you get trained. So next things will become easier. Remember, the first spelling that you did was the hardest. After that, things became easier, in a sense easier, although they were really not easy. So it's almost the same thing. So we'll come to these structured things then, and then finally with numbers. And by the time as we go, we will see several. That was the idea of my write-up, to uncover very fundamental things which we will assume. For instance, we will show that we have till now not questioned what are natural numbers. So the whole idea is to give a formal justification of natural numbers, and that's why, and many others we will see, many other gaps will come up, and that will actually lead us to the axiomatic development. So that is the whole course about. So we will spend one more lecture on this section 8 next day, surely. And if you still feel a little more is needed, we can do that. And then we will proceed to the next section. So Next week we should be completing everything up to this section in pre-order section 9. So everything up to section 8 must get cleared up. So that is my idea. What do you think? Yeah? Things from you?
I'm comfortable.
I don't see a problem with it, though. I think it's all right.
Okay. Roughly, there's another thing. Now things. It was always like this, but it seems that now UNISA is hell bent on having certain documents. So possibly I will send you a PDF file about. It is called midterm student evaluation. So. I don't see others, so I think I would send it around in the email because Thandekile and what's the other lady? They have not joined in this group and they are not joining us. I don't know whether they have left or not. I don't know. So I'll send this around. And please send back your replies to it. I don't have any problems even if you consult between yourselves or with others or whatever, but UNISA says that it must be done by the person individually. So, this is one of those boxes that must be ticked, so I'll send it around and please submit it by this week. So that I'll also have to submit by the end of this month. Okay. Yeah. Anything that you have to say? Any questions, queries from your side? Yeah?
No, I'm covered, Doc.
Okay. So, if so, then let's meet next time. Keep well.
Thank you very much, Doc.
Thank you.
Thank
Bye.
you.